Hello EPC Mechanics students. In Unit 6 Oscillations, Class 1 6.1 Simple Harmonic Motion Harmonic Oscillator Part 1. Then Section 1 Oscillatory Motion Simple Harmonic Motion. Oscillatory motion is any repetitive back and forth motion around an equilibrium position. One specific type of oscillatory motion is simple harmonic motion. Simple harmonic motion is a repetitive motion under the influence of a restoring force where the acceleration is proportional to the displacement. The restoring force always points toward the equilibrium position. Now this is very important. Anytime throughout this unit, when we refer to simple harmonic motion, we need to cite the following two facts: that the acceleration is being proportional to the displacement, and there is a restoring force that is always pointing toward the equilibrium position, which is driving these oscillations. Some good examples of simple harmonic motion is a horizontal oscillator, vertical oscillator, and simple pendulum. And other examples will be visited too throughout the course. Since the acceleration for such systems is proportional to the velocity, no, this should be to the displacement. Then the dynamics of such systems is not trivial. Now why I have written here to the velocity? Because previously in Unit 2 we have seen dynamical systems in which the acceleration is proportional to the velocity under the influence of a drag force, and we have seen that to deal with such type of systems is not trivial, and we need to promote the equation into a differential equation. Another complicated systems is whenever the acceleration is proportional to the displacement, and as we shall see, specific case given by the simple harmonic motion. Now in this case, if you think about it, the acceleration is proportional to the displacement or the velocity, which means they are not constant, and we cannot deal with them using kinematics. We need to deal with them using the calculus approach. The aim of this unit is to investigate the evolution of these systems via different approaches. Now Section 2, Parameters of Oscillatory Motion. Previously in Unit 1 we have introduced parameters related to repetitive motion, and here we will review them again. For a repetitive motion we can always define the following quantities given by the period frequency, the angular frequency. The frequency f hertz is the number of cycles per second. The period is the time required to complete one cycle. The frequency and the period, and from their definitions, if you think about them, because they are related to the cycles, this is per second and this is the time needed to complete one cycle. They are reciprocal to one another, and we can define them as follow: that the frequency is the 1 over the period and the period is 1 over the frequency. Now here from this animation we can notice that as the frequency decreases, the speed along which the particle is traveling along this repetitive motion decreases, which means the speed indeed reflects the number of cycles per second. And as the period increases, this means that it's gonna take it more time to complete the cycle. For this reason, we are referring to these two definitions. Now the angular frequency omega is defined as 2 pi f, which is 2 pi over t, and its SI unit is radians per second, rad per second. Now Section 3, Horizontal Oscillator, Equilibrium Position, Amplitude and Cycle. Now a horizontal oscillator is formed by connecting a spring of stiffness K to a fixed support, and from the other end we connect a mass M that can move horizontally on a level surface. So basically here we have the following arrangement. This is the level surface, that's the spring, that's the support, and that's the mass M connected to the spring. The spring performs oscillatory motion under the influence of the restoring force. Now here the restoring force is the force provided by the spring on the block. For example, if the spring is ideal, Hookean spring, then the restoring force is governed by Hooke's law. Now what is it, the equilibrium position? It is the point where the restoring force vanishes momentarily. It is usually the symmetric position between two extreme positions given by the amplitude. So basically that's the equilibrium position. Often the origin is chosen at the equilibrium position, and it happens that for x equal to 0, it's the equilibrium position. Now X here represents the position of the block, and we know if we're talking about a Hookean spring, then the force provided by the Hookean spring is given by F is minus kx, and remember that this sign represents that the force is a restoring force. So we assign that x is equal to 0, the force vanishes momentarily, and it happens to be the equilibrium position, which is here. That's the equilibrium position. Now the amplitude, it is the distance from the equilibrium position to an extreme position and denoted by A. So basically that would represent the amplitude, or even half the distance of two extreme positions. So basically this is an extreme position and this is an extreme position. The distance between two extreme positions would represent the double of the amplitude. Recall that even position might be positive or negative, but amplitude has been introduced in terms of distance, then amplitude is always positive. Now, if that's the origin, any position to the left of the origin would be negative. Any position to the right of the origin would be positive. However, amplitude, even if we're measuring it to the left, amplitude is always a positive quantity. Now here in this case, if we want to plot x versus t, now here we're talking about specific type of motion, which is simple harmonic motion, that we will later refer to it. Now the equilibrium position would represent these points in which the position becomes 0. So these along the oscillation represents the points of the equilibrium position in which the block passes through the origin and the restoring force vanishes momentarily. And these would represent the amplitude. So here we can notice that the amplitude is constant, and we will talk about that later because there is no friction, and the amplitude for this particular example is given by 20 centimeters. So the amplitude is the distance from the equilibrium line to the peak. Even you can measure the amplitude here in this case from the equilibrium line to the lowest point reached by the curve, but in this case the amplitude is given by 20 centimeters and not minus 20. But the position is negative 20 centimeters. Now what about the cycle? It is one identical repetitive motion and it is identified by 4 amplitudes. Example 1. Starting from B. Then we're going from B to O to C to O to B to form a cycle. Let me illustrate more. So here we're referring to the cycle as 4 amplitudes. So how can we identify a cycle? So suppose we started, let me say that this is B and that's C. Now, how can this block perform one complete cycle? So if we start from B, we need to go from B to O, which is an amplitude, O to C, another amplitude, C to O, another amplitude, so that would complete 3 amplitudes, and O back to B, which completes a cycle given by 4 amplitudes. Now suppose we have started from O, and this is a bit challenging, I will explain why. Now the cycle would be O to C, O to B, then back to O, and that would form a cycle. So suppose we have started from this point. Now remember that a cycle is 4 amplitudes. And don't think about it that if the block returns back to its original position, that would represent a cycle. Let me explain more. So going from O to C, so that's B and that's C. Okay, that's an amplitude. Now going from C to O, that's another amplitude. And one might think of this would represent a cycle because we have returned back to O. No, that's not correct because this represents 2 amplitudes. Now going from O to B and going back from B to O, that would complete 4 amplitudes and that would represent a cycle. Another example, example 3, starting from C. So if we started from C, now C to O, this is an A, O to B, this is another A, B to O, that's another A, and O back to C, that's another A. So 4 A's representing 4 amplitudes, that would represent a cycle. And now how to measure the period using the graph. Now notice carefully that the graph is given by the position as function of time. So if we do the measure along the horizontal axis, that would give us the period, but how we're gonna do that? Now let's consider the following 2 dots. Remember that we have stated previously that the period is a cycle and the cycle consists of 4 amplitudes. Now from these 2 peaks, count with me, this is an amplitude, this is another amplitude, that's another amplitude, and that's another amplitude, forming 4 amplitudes. So if you measure the time from these 2 consecutive peaks, that would work and would give you the period. So in this case, the period is given by 8 seconds, which is 10 minus 2. Now another good example is that from these 2 dots. Now this would represent a period, amplitude, 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 amplitude. So 4 amplitudes, which represents a period. And if you do the count from this dot to this dot, so 14 minus 6, that would be again 8 seconds. So here we have investigated how to measure the period, which is from 2 consecutive peaks or from the 2 bottom dots. Now what about if we need to measure the period from the center? Now that's an amplitude, 2, 3, 4. So the time from this dot to this dot, which would represent the period, and if you do the count, that indeed would be 8 minus 0, which is 8 seconds again. Or we can measure them from these 2 dots, so that's a period, amplitude, 2, 3, 4, and 16 minus 8, that would give us again 8 seconds. And if we measure the period from the yellow dots, again, that's 1, 2, 3, 4 amplitudes, and 12 minus 4, it would be 8 seconds. So what do we conclude here? If we're measuring the period from the peaks, so the period represents the time between 2 peaks, and as well as the bottom points. Now if we're measuring from the center, we need to choose a point, skip a point, and choose another point that would give us the period, because we need to form 4 amplitudes. Now section 4, simple harmonic motion, the equation of motion. The aim of this section is to determine the differential equation that governs the evolution of the system for a simple harmonic oscillator. And whenever we think about differential equation, it means that we need to use a big law, either Newton's second law or conservation of energy. For that, consider a horizontal oscillator formed of a block of mass m and a spring of stiffness k. The block is connected to the spring, and the other free end of the spring is attached to a support, thus forming the horizontal oscillator. Consider a point along the motion of the oscillator between the equilibrium position and the amplitude. So that's the equilibrium position in which the point the restoring force vanishes momentarily, and that's the maximum position to the right reached by the block. Let's assume that the spring is ideally governed by Hooke's law, given by F is minus xk, so this is a linear spring, and neglect all frictional forces. Now remember that always, because this is a restoring force, the force would be pointing toward the equilibrium. Even if the block is here, the force would be pointing like that. The forces that are acting on the block would be the pull of gravity down, the normal push up, and the tension in the spring. So here we're doing the FBD for this particular position. If we wish to do the FBD for this particular position, we know that the pull of gravity would be down, normal pushes up, but the thing is that the force of the spring would be pointing toward the right. Note that the tension always point toward the equilibrium position, and now we can apply Newton's second law after utilizing the forces that are acting on the block. We have F net is ma, Fg plus Fn plus Fs is equal to ma, and now we're gonna project along the horizontal. So remember, this is a vector equation. It gives the birth of 2 linear equations. Now we're interested along the horizontal direction. The pull of gravity has no projection, as well as the normal push. The spring would be given by minus x. Now here, notice that this has nothing to do with the thing whether it's positive or negative, but just because it's a restoring force. Okay, for a very simple reason, you can apply the vector relation here and the projection when the block is in this point. So the force of the spring would be pointing toward the right. This doesn't mean that this should be plus. No, that's wrong. Here, the way to deal with such projections is to utilize that this is a restoring force, and you should include the minus sign as we used to do with the drag force. Now the thing is that we have, okay, so the minus sign indicates that the force is restoring force. Now we have 2 variables given by x and a. We wish to find x. Now no other equation that can be implemented in order to solve for a, like the Atwood machine, or x. So the trick is to convert this equation into differential equation, and this is achievable. Why? Because x and a mathematically they are related via calculus. So in this case, minus kx is equal to md square x by dt square. So moving this to the other hand side and reading the equation from right to left and dividing by m, because we would like the derivative always to be normalized of coefficient 1. Then the equation of motion for a simple harmonic motion horizontal oscillator is a second order differential equation in the position x. Here notice carefully that we call this type of equation a differential equation of second order. Why? Because this is a second derivative. Unlike for the drag force, for the differential equation of velocity, it was a first order. In the dot notation, so if we assume that the dot means the derivative, this can be written as x double dot plus k over m, x is equal to 0. Double dot, it means the double derivative of the position. A lot of physical interpretation can be extracted from this differential equation. Then let's start interpretation. Physical quantities cannot be added or subtracted unless having the same unit. Then comparing both fractions of the differential equation. So notice that here on the left hand side we're adding two fractions, which means that these two fractions should agree dimensionally. It means that they should have the same unit. Now, rewriting this fraction in the form of x over m over k, let's analyze the units. Now, d square x has a dimension of position which is meter y. Now, although here we have a power 2, but this is for the operator and not for the position. So, dx has unit of meter, d square x has unit of meter. However, dx square has unit of meter square. Now, dt square has a dimension of time square, which is, let's assume, second square. So dt has a dimension of second, dt square has a dimension of second square. However, d squared t would have the dimension of second. Now, so while we're doing that, remember that we said that fractions cannot be added or subtracted unless they have the same unit. Now notice that because this fraction, the numerator has a dimension of meters, which means that the denominator, which is m over k, should have the dimension of second square. And since we're talking about repetitive motion, then this fraction, which is m over k, that represents the dimension of time square, should be related to the period of the oscillator, which is time square. Then it is found that the angular frequency omega and the period t of a harmonic oscillator characterized by mass m and stiffness k is given by omega is equal to square root k over m, but omega is equal to 2 pi f and 2 pi over the period. Then the period is given by 2 pi over omega, which is 2 pi over square root k over m, which is 2 pi square root m over k. Therefore, omega is given by the square root k over m, and the period is given by 2 pi square root m over k. So you can ask yourself, how did you obtain these two expressions for omega and the period? One way to convince yourself is using dimensional analysis that I have done here. So omega and the period, they depend only on k and m for a horizontal oscillator. Also, the differential equation can be represented as x double dot plus omega square x is equal to 0y, because if we have identified that omega is equal to square root k over m, then omega square is equal to k over m, and this differential equation can be written as x double dot plus omega square x is equal to 0. The period and the angular frequency only depends explicitly on the mass m of the oscillator and the stiffness k of the spring, and this is not an intuitive result. To illustrate more, suppose two oscillators of the same mass and stiffness k are set into oscillation with different amplitudes a1 and a2. So now suppose here we have two oscillators, they have the same stiffness k and they have the same mass. We're gonna drive this oscillator with an amplitude a1, we're gonna drive this oscillator with an amplitude a2, and a2 is greater than a1. So one can ask which one has the greater or the smaller period. The thing is that the period only depends on m and k. So as long as you don't break the Hookean limit and the amplitudes are different, both oscillators will have the same period, because the period and omega only depend on m and k. Since m and k, they are the same, then they have the same period. The period, okay, the acceleration a, so remember that at the beginning we've stated that for a simple harmonic motion, the acceleration should be proportional to the position, and there should be a restoring force. The acceleration A of a harmonic oscillator is proportional to position x as seen from Newton's second law, because remember that from this equation we can write acceleration as minus k over mx, which means the acceleration is proportional to the position. For this reason, this is a simple harmonic motion. And this is how we define the simple harmonic motion. Acceleration is proportional to displacement. This is an important result, which means that the acceleration is not constant, it is variable. Since the position x is variable, then always and forever don't think about kinematics here. You can only think about calculus. Then kinematics related to uniform and uniform varied motion breakdown, and the way to proceed is only via calculus. Now, section 5, solution of second order differential equation, the simple harmonic motion. If you think about the differential equation given by x double dot plus k over m x is equal to 0, then we're searching for a solution which represents an explicit function of position in terms of x is x of t. So remember, in the drag force, such type of equations can be solved by integration, but this could be done in the case of the drag force because we have first order derivative. Here we have a double derivative, so we cannot integrate. It will be difficult for us to integrate twice. So a function that can be derived twice and can vanish its original form, gives you back its original form, would be perfectly described by trigonometric function. So here we are searching for a function that can be derived twice, such that when you add it to its original function would vanish. So if you consider, for example, the sine function, the derivative of the sine would be cosine. So this is the first derivative. The second derivative would give you minus sine t. Now this negative sign, whenever added with the position, we would end up having a 0 up to a sum constant. And remember that whenever we're deriving, if this is a linear function, if we derive, we need to multiply by the inner derivative. So here we should add some constant. So the solution, the general solution, would be given something like that. Both solutions are equivalent and they can be linked to each other via trigonometric relations. So this trick works for both, for cosine and sine. Now we need to define what does xm, omega and phi represent. Now x of t is the position of the oscillator and the solution of the differential equation. xm is the amplitude of oscillations known by also a, m in meters. So xm, the coefficient here, is the amplitude, also have been identified previously by capital A. Cosine omega t plus phi or sine omega t plus phi are modeling functions. They are dimensionless quantities. So the cosine and the sine, they don't have any unit. Omega is the angular frequency, as we have defined previously, and phi is the initial phase difference and can be determined based on initial conditions. Remarks: any differential equation that satisfy the form x double dot plus omega square x is equal to 0, then the system obeys simple harmonic motion. So if we're determining the differential equation for any dynamical system, and if we have achieved this form, this means that the type of motion is simple harmonic motion. Also, such type of motions given by trigonometric functions are known by sinusoidal motion. And now for the rest of the video, we're gonna solve some exercises. Exercise 1, which of the following is a differential equation that correctly describe Newton's second law for a simple harmonic oscillator of mass m and a restoring force constant k? So we know that it's given by minus kx, is given by m a, so which is minus kx is equal to m d square x by dt square, making B to be the correct answer. Now an object undergoes simple harmonic motion along the x-axis shown above, where x is 0 is the object's equilibrium position. Which of the following graphs best shows the relationship between the object's acceleration a and its displacement x from the equilibrium? Assume positive a to be acceleration directed to the right. So remember that from the differential equation we have minus kx is given by ma, which means that a is given by minus k over mx. Then if we're plotting a versus x, then the shape of the curve would be a straight line with a negative slope, which means a is the correct answer. Now the equation of motion of a simple harmonic oscillator given by d square x by dt square is minus 9x, where x is its displacement, and t is the time. The period of oscillation is what? Now we know that the differential equation has the form of x double dot plus omega square x is equal to 0, and this can be written as x double dot plus 9x is equal to 0. Now comparing both equations, which means that omega square is equal to 9, which means that omega is equal to 3 radians per second, but we're interested in the period. We know that omega equals to 2 pi f, which is 2 pi over the period. This means that the period is 2 pi divided by omega, which is 2 pi divided by 3, making D to be the correct answer. And now finally, exercise 4 as an exit ticket for today's video. The motion of an object undergoing simple harmonic motion is formed to obey the differential equation. So you notice that whenever we're talking about simple harmonic motion, it should have the following form. Now we're interested in the frequency. So we know that x double dot plus omega square x is equal to 0. And this can be written as x double dot plus 4x is equal to 0, which makes that omega square is equal to 4. Then omega is given by 2 radians per second, but we're not interested in omega, we're interested in f. Omega is equal to 2 pi f. Then f is given by omega divided by 2 pi, which is 2 divided by 2 pi, and that would be 1 over pi, and the unit of the frequency is hertz, making A to be the correct answer. So that's it for me in this video, guys. See you soon in a new one.